antenna by the transmitter. So that will create the oscillating magnetic field. So around the antenna element, right? And as well as the charge of electrons is also going to create the oscillating electric field. Both are time varying in nature. So this time varying fields is going to move away from the antenna as a electromagnetic field, right? So this is during the transmission. When it is during the reception, the oscillating the electromagnetic fields is going to exert a force on the electrons on the antenna elements. So when this force is exerted, then automatically it is going to create the oscillating current inside the antenna. So in this way, the EM is converted into oscillating current, right? So there are major types of antenna, transmitter and receiver. So out of which, based on the radiation pattern, it is of two types. One is omnidirectional and another one is directional antennas. So when it is going to be omnidirectional antennas, then the antennas is going to emit the radiation or receive the radiation from equally equally from all the direction. When it is going to be directional antenna, it is going to transmit or receive the signal or the electromagnetic radiations from a particular point or region. So this is called as the omnidirectional and directional antennas. And there are two types of fields. One is near field and second one is the far field. So let us consider an antenna. That antenna is enclosed by a smaller field, right? The region within that antenna is called as the near field, and the region outside that sphere is called as far field. Usually, the antenna characteristics are measured in terms of far field regions. Right. So it is widely used in many applications, but the near field applications and far field applications, there are plenty of applications with respect to antennas. Out of which, the short distance communication through water, underwater communication, and soil are the important application nowadays. It is emerging, right? So that is the major, and also the 5G communication also requires different types of antennas based on some criteria. Still, there are a lot of scope and lot of research gaps available in this areas. So if you are going to work with antennas, you can choose this areas. This areas have a wide variety of scope. And already I have explained about the directional and omnidirectional, how this radiation is going to be there, how the radiation is going to be there. So this radiation, so in ideal condition, so all the incident energy will be reflected back when it is going to be the open circuit, right? When it is going to be open circuit, since antenna is the open circuit, is open to the environment, right? So ideally, all the incident energy should be reflected back, but practically, some portion of electromagnetic energy will be escaped. So that portion is very small in number. The reason is the mismatch between the transmission line and the free space. So in order to match the impedance, match the impedance between this transmission and free space, there is an enlarging. There is an enlarging which is called as flaring, which is called as flaring. Such flaring can able to improve the impedance matching between the transmission line and free space, and as a result, the impedance is matched, and automatically coupling between the transmission line and free space is improved. So the entire radiation efficiency is going to be increasing, right? So which is similar to a maximum power transfer. The maximum power transfer will be term. So the maximum power transfer will be done when the source impedance and load impedance are equal, right? So that is the concept here, right? So with respect to all these type of antennas, this microstrip antennas has a wide variety of applications. So that I will share here. So this microstrip antenna, so it is a printed antenna. So it is going to have a dielectric substrate. On top of the dielectric substrate, it is going to have a radiating patch. On the bottom, it is going to have a ground plane, right? So on one side, it is going to be the radiating patch. On the other side, it is going to be the ground plane. So the patch is generally made up of conducting material. The patch is generally made up of conducting material such as copper or gold. Since gold is costly, the copper is widely used. So the patch has a thickness of very thin, right? The patch is going to be very thin, and its value is very less than lambda naught, and usually it is 0.003 lambda naught to 0.005 lambda naught. So within this range, the patch thickness should be there, and the microstrip patch is designed such that the maximum radiation is in broadside direction. The maximum the radiation is broadside direction, that is perpendicular to the antenna axis, perpendicular to the antenna axis. This can be accomplished. So how it is going to be accomplished? So it's by choosing the current excitation beneath the touch and field configuration. We have variety of substrates used in the used for designing the microstrip patch antenna, and substrates has the dielectric constant which is varied from 2.2 to 12 of relative permittivity, right? So that is what the substrate is. The variety of substrates is that, like FR4, Roger, R2, so everything is available, and that in that the FR4 is widely used since it is easily available and cheaper in cost, and it is somewhat have some good performance, not better performance. It is average performance. It is going to have some average performance when compared with the other substrates. But the major reason why the choosing the FR4 is it is cheaper in cost and it is going to have it is easily available. That is the two major reasons. And with respect to the performance improvement, the thick substrates is going to have a very good desirable antenna performance, and also the dielectric constant should be very low. So when this two condition is achieved, better efficiency will be there, and larger bandwidth is going to be there, and loosely bound fields of radiation into the free space can be there, but the element size will become larger. That is the major problem. And if there is going to be the larger, then there is going to be very larger substrates, then automatically the size of the antenna is going to be increased. That is what it is mean. And microstrip antenna is going to primarily radiate with the help of the fringing fields, so which is actually available at the discontinuities. Which is also actually available at the discontinuities of the microstrip patch, which is available in between the patch edge and the ground plane. So the radiation will be increases with thicker substrates and the substrate with lower permittivity, and it is going to originate from at the discontinuities. And these antennas can be easily integrated with the microwave integrated circuits. When they are going to integrate with it, the antenna performance and the circuit design has some compromise. There is some trade-off. And the radiating elements and the feed lines is going to be photo etched on the dielectric substrate, right? The radiating element can be of any size and any shape. The size is going to decide the frequency, while the shape can be of any type. Maybe it is a square or a rectangle or even a dipole or circular, elliptical, triangle, or any configuration can be of the radiating patch that can be used. And this another advantage is it is versatile in nature. It is versatile in nature. So for any wide range of frequency, we can able to design the microstrip antenna, and we can able to have some polarization patterns as well as the impedance matching the values. And it is widely used in mobile and government security systems where very narrow bandwidth is going to be there. So narrow bandwidth is the major disadvantage. So that any application which requires a very narrow bandwidth, this microstrip patch antenna can be utilized. And there are variety of techniques have been available in order to increase the gain and increase the bandwidth, and in order to improve the antenna performance. So this are the major points I have to share with respect to the microstrip patch antenna. And some other features are it is going to have a low power handling capacity and high quality factor and poor polarization purity and poor scan performance and narrow frequency bandwidth and low efficiency. These are some of the features, and they are also nowadays used with microcomputers, laptops, and mobile phones. So, and several desirable qualities are the broadside radiation pattern. So, with the help of broadside radiation pattern, it can be integrated into two-dimensional arrays. The array formation is quite easy with the microstrip patch antennas, and then the antenna is going to have a very low profile and very low cost, and conformability is very good, and the manufacturing is not at all an issue with respect to microstrip patch antennas. And then it can be integrated with microstrip as well as the coaxial cables and probe feeding, And then multi-layer schemes can be done with the multi-layer antenna can be what we can be able to design, and different also it can able to support different types of uh, also it can able to support the different types of CPW, different types of feeding like CPW and district line. So variety of techniques we can able to do. So that is the major advantage with respect to the um, uh, microstrip patch antennas. And the next one is the patch antenna with microstrip feeding is widely used. So on comparing with variety of, I will show some of the feeding techniques. On comparing with this feeding techniques, the microstrip patch antenna with the patch antenna with microstrip feeding is widely used. And feeding is extremely important since it is going to decide the bandwidth, cross polarization, and ripple factors. And this microstrip feed patches is going to have a very narrow bandwidth, so which is less than 5%, which is almost less than 5%. And there are variety of improvement techniques that is available in order to improve the bandwidth. So one by one I can able to show you. So it is also called as patch antennas. It is widely used above 1 gigahertz, and hence it is also called as gigahertz antennas. And then so this is the radiating element, and this is the feed line, and you can able to clearly see this is the substrate, this is the SMA connector through which the input can be given. So this is the another method by which the coaxial feeding from the bottom the feeding is going to be there. So the feed line is from the bottom, from the ground, it is penetrated into the dielectric and it reaches the top of the patch. So in this way the feeding can be done. So anything can be used, and the common shapes are the rectangular, square, circular, annular ring. So these are the variety of shapes. And in 1972, the Bob Monson is discovered this. And some of the advantages are it is low profile, it can be easily fabricated, easily fed, it can be integrated with the microstrip circuit elements, and pattern is with moderate directivity is achieved, and it can be easily converted into arrays, right? So another disadvantage with respect to this microstrip antennas are it is going to have a very low bandwidth, and the efficiency is very lower when compared with other antennas, and it can be used only at microwave frequencies. It cannot able to handle very large amount of power, right? So this is the rectangular patch antenna. Here it is the ground and it is the dielectric. On the top of the dielectric it is going to be the rectangular, and hence the rectangular radiating element, and hence it is called as rectangular patch. And instead of rectangular patch, when you are going to have the circular patch, then it is called as circular antenna. Right. So now it is with respect to feeding. So the first feeding is the coaxial feeding. Then the coaxial feeding, while designing when you are going to design the antenna and the CST using the coaxial feed, then you have to make sure that the inner conductor is penetrating through the ground, through the dielectric, and reaches the top position of the feed, that is the radiating element. And the outer conductor should be connected to the ground plane. So this is what the coaxial feed is. This is how the coaxial feed is. And this is the insert feed, which is the which is similar to a microstrip line, but the major difference is there is an insert here, there is a slot here. This slot is going to be available in order to match the impedance, right? In order to match the impedance. When there is no slot, then it is called as microstrip line. When there is going to be the slot, then it is called as insert feed, right? It is simple. It is going to be the planar feeding technique, and it can be easily integrated into arrays or converted into arrays, and input matching is very good. But the major disadvantage is when the notch is going to be very large, when the notch is going to be very larger, the patch current and radiation pattern is going to have some distortion. That is the major problem. And then with respect to proximity coupling, so the microstrip line is going to be sandwiched between the two dielectrics. On top of the dielectric, it is going to be the patch, and the bottom it is going to be the ground plane. With the coupling only, the patch is going to be excited. So the major disadvantages, it is going to require the multi-layer fabrication, and alignment is also a problem. But the advantage, it is going to have a very higher bandwidth. That is the one of the most important advantage when respect to the proximity coupled view, right? So if your application require a larger bandwidth, then you have to go with the proximity couple. And then gap couple, and here the major problem is It is similar to a microstrip line, but there is a gap between the patch and the field line. The major problem while designing, the gap has to be correctly maintained, otherwise the performance will not be achievable, right? So require accurate gap fabrication. So high impedance also can be matched with respect, the impedance is going to be high with respect to the circuit elements, then automatically we can go with the gap couple. High circuit impedance can also be matched with the gap couple field, right? So the two major disadvantages with respect to the microstrip patches are, one is gain and another one is lower gain and another one is the narrow bandwidth. So in order to improve the gain, the effective area can be improved, right? So with the help of by increasing the effective area, we can improve the gain. So that effective area can be increased by meandering of edges or parasitic patches. And then we can make use of the EVG materials and the metamaterials in order to improve the gain. And in case of antenna bandwidth improvement, the substrate height can be increased, but the substrate height should not be should not be, there is a value, so it should not be greater than 0.25 of the resonant length, right? 0.25 of the resonant frequency, resonant wavelength, that is resonant guided wavelength, lambda g. So that is what the thing is. We cannot able to increase the substrate height as our wish, that we have to see it in detail. We have to stick to the things. And then DRA can also be used in order to improve the bandwidth, and the slots and the partial grounds are some of the important ways by which the bandwidth can be improved, right? So what is the effect of the dielectric? If the epsilon r is going to be very low, that is the relative dielectric constant is going to be very low, both the length and width is going to be increased. When the length and width is going to be increased, the size of the antenna will be increasing. So when the length and L is going to be increases, it increases the fringing feeds and the aperture area. So as a result, the gain and bandwidth is going to be increases. When we are going to increase the epsilon r, then automatically the length and width is going to be decreased. When the L and W is going to be decreased, the size of the antenna is going to be decreased for the same resonant frequency, but the gain is going to be decreased. So there is a trade-off between the size of the antenna, gain, and the so this is the some of the observations from my research point of view that can be implemented in your design, so that you can able to achieve some improved gain and bandwidth, right? So this is the formula for the rectangular patch antenna. So the length and width, effective length and effective width is going to be there. So there are two variables. One is C, which is 3 into 10 power 8, and then the resonant frequency of your application, and the epsilon r, which is the dielectric constant value. From this, you can able to find out the W value. On substituting this W value, you can able to find out the epsilon E value. So this epsilon E can be utilized here in order to find out the del L. So from this del L, you can able to find out the L value, and then the W value can also be easily from W and del W, you can able to find out the W value, and from that you can able to easily solve it. And then with respect to the circular patch antenna, this is the formula we have to use in order to design the value. Here also the two values, one is epsilon r value, and the next value is the resonant frequency value, where H is the effective height of the substrate, and with respect to epsilon E, the formula is this formula. You can use this formula, and you can able to find out the radius of the circular. So and then the equalator triangle. So this triangle is going to have again the resonant frequency formula. So where the side length can be found out from S equal to plus 4h by root of epsilon r. So this epsilon r is going to give the value of the dielectric constant, and h is the height of the substrate. From this you can able to find out the side length. So these are some of the important formulas. So there are variety of designs in the microstrip patch antenna, but when compared with this, the circular geometry of patch antenna is going to have a very more compact than rectangular or any other type of patch antennas. The circular geometry is going to be more compact, and the freedom is also only with respect to the radius. Only with respect to the radius, there is going to be only one dimension, which is called as the radius. So this radius is going to decide the resonant frequency. So that is why the circular geometry is widely preferred on comparing with all the other type of patches. The rectangular are widely used, and out of which the circular is going to be more compact when compared with the rectangular patches. Right. So this is the antenna what we are going to design today, right? So this is the simple microstrip patch antenna, and it is going to have a ground. So this is the substrate, and this is the front view, and this is the back view, and this white color is the substrate, and this yellow color is the ground, and this is the radiating circular radiating element, and this is the feed line, right? So this is the first we are going to have a full ground, that is, so here the width of the ground is W, and the length of the ground in this design is LF, right? The length of the ground is LF, but first we are going to design the full ground, that is the length of the ground as L, right? The length of the ground as L, and then after that we are going to reduce that L value to LF, so that the ground is going to be somewhat defected in nature, not defected, reduced in nature. So we have defected is different from reduced ground, and then we are going to insert the complementary splittering resonator. Then we are going to insert the complementary splittering resonator. Because of this insertion, what is the effect we are going to see? So these are the dimensions, various dimensions of the complementary splittering resonator. So this is the optimized dimension which I already designed, and that design is what we are going to see today. We are going to have it as a demo, and after that, what I am going to have is, in order to improve the gain, I am going to have a superstate with metamaterial, with SR splittering resonators on top of the superstate. So this is the actually this side view of this antenna. So on from at a height of 0.8 mm, right? At a height of at a height of 1 mm. That is the distance between the antenna and the superstate is 1 mm. So at that height, the superstate is designed. So on top of the superstate, this splittering resonator is going to be included. So this splittering has the dimensions here, and then we are going to see how the superstate is going to help us in improving the gain. So this is what today we are going to see. So we will start designing the CST Studio. Parallelly, during the simulation, I will share you some of the basics about the metamaterials and some of the things with respect to the 5G. Actually, this antenna what we have designed is going to operate from 3.6 to 4.2, which is for the 5G application, which covers that band. Apart from that, another band at 2.1, I think so, and so on. Another C band application is also going to be there. So this multi-band, so out of which this band, this 5G band is going to have a very high bandwidth with very good bandwidth impedance. That will be, so I will share some basic details about the 5G requirements also. So I hope this session will be useful for you. So just a second. Whether the CST Studio software is visible to you?
Yes, sir. Yes.
Yes. Thank you. Right. So this is the CST Studio window. So here you can able to view. There is an option called Create Project. Just you have to click it. So on clicking it, another template window, workflow window is going to be there. So with respect to CST, we have plenty. It can be used for plenty of applications, from static low frequency, so low frequency devices, from electromechanical devices, magnetic design, sensor, EMC shielding, and power electronics, and high voltage and heavy current transformers can be designed. Everything can be designed. And then with respect to the microwave, RF and optical, antennas, circuits and components, filters, couplers, isolators, circulators, everything can be created in circuit and components, and radar cross-section. And then the biomedical, important part of biomedical wearable devices can be designed here, and optical application and periodic structures like FSS, metamaterial unit cell simulations, everything can be done, right? And optical application, we have some applications also, terahertz application. And then with respect to the EDA, PCB package, chip connectors and cables can also be simulated. With respect to EMC, EMI, radiated emission, conductor emission, radiator susceptibility, radiated conductor susceptibility, and PCB checkings and components checkings can also be there. So such simulation can be available. And with respect to charged particle dynamics, so vacuum electronic devices can be there, and beam optics can be analyzed, and even space applications is also going to be utilized, can be analyzed, and like TWT and magnetron and Klystron, that such devices can be easily designed in terms of the charger particle dynamics. So everything can be is available in a single software. That is the advantage of the CST Studio. And then and for each thing we have a separate workflow. That is the another advantage. So we can just go into that workflow, and which will guide us easily to complete our requirement, right? Our simulation. That is what the major advantage with respect to CST while comparing with all the other softwares which is available nowadays, right? So that is the major advantage. And this microwave, RF and optical, I am going to choose, since I am going to design the antenna. So in the antenna, click on next. So in the antenna also, again the workflow will be there, and based on our application we have to choose. When you are going to design a dielectric resonator, you have to choose the dielectric resonator. When you are going to design a waveguide, that is a horn antenna or a cone antenna, then you have to click on the cone antenna. And when you are going to design a PIF antenna, planar inverted F antenna, then you have to click on the mobile phone and integrated devices. So such thing you have to click on it. So here I am going to design a patch antenna, so I just click on the planar antennas. Just click on it, click on next. And there are three different types of solvers that can be recommended. One is time domain, and another one is frequency domain, and the next one is the multi-layer application. Next one is the multi-layer application. There are the three different types of solvers which is going to be available. So the first one is time domain. This time domain can able to analyze the antenna for wideband as well as multiband application. For both wideband as well as multiband application, it can able to easily analyze, right? So that is the first advantage. And when you are going to have design an antenna, which is when you have to analyze for that particular resonant frequency, then you have to go for the frequency domain. When the ground planes are multiple and infinite, as well as when you are going to use a zero thickness methods, then you have to go for multi-layer solvers. So usually this time domain and or multiband is going to the basic solver just choose. All the solvers is going to give the same results only. But what is the design consent is going to be decided. And with respect to the dimensions, so when you are with the help of equation, you have just designed the dimension, you have arrived at the dimensions. When you are going to calculate the dimensions in centimeter, you can choose it here, right? So I have chosen the calculated dimension in mm, so I have just chosen as mm. And the frequency of operation, you can able to change it here. So in the gigahertz frequency range only, I designed that antenna. So just click on gigahertz and click on next. And the minimum and maximum frequency should be the frequency. Should it be a band of frequencies? In that band, your operating frequency antenna should be available, right? For example, if you are going to design an antenna for 5 gigahertz, you have to give the minimum frequency such that the 5 gigahertz should be available between the minimum frequency and maximum frequency. So I am giving here 1 to 8. 1 to 8. Minimum frequency as 1 and maximum frequency as 8. And click on next. And finish it. Right. So this is the window. This is the design window. So in this design window, we have to design the antennas, right? So that this folders I will explain one by one while designing the antenna. Otherwise, the time constraint is there, so I have to keep that time. So I will give the details when I am utilize that tab, right? So here this is the design window. So in this design window only we are going to make the design. So here we have some views, different types of views. This is the perspective view, three-dimensionally we can view the window, and this is the front, and this is the back. So after designing, we can able to clearly see it, and this thing. So this arrow mark you can able to rotate it in any shape, right? After rotating it, you can able to uh, keep it in front side. So this box is called as bounding box. So this box is called as bounding box. So this box is nothing but the air box, which is already available, and it can able to this CST alters the size of the air box based on the designed antenna, based on the designed antenna size. It automatically updates. The CST automatically updates. So the use of this box, it will convert the near field data with the help of Fourier transforms. The near field results, while simulation, the antenna is simulated, near field results will be available. With the help of Fourier transform, the near field results is converted into far field results. That far field results is available at the result tab, right? The use of this airbox is in order to convert the near field result into far field result. That is what the use of the airbox. So this is with respect to the uh, application window, sorry, design window. And this is the navigation tree. So while designing each step, this component will be updated. So designing the ground will be available here. After substrate, the substrate will be available here. So this is the design navigation tree. And the result after simulation, the results will be available at this part. So this is the result part. And then the message. So during so this progress, while giving the start simulation, the progress window will show us what is the progress of the simulation, and this message window after the simulation over, the message will be available here, and then the parameters. So these are the various parameters. So these parameters are nothing but this is the values. So this values is called the parameters. So the design parameters has to be updated in this window. The design parameters has to be updated in this window. So this is what the first stage is. So this is about the various types of tabs available. One is navigation, and next one is message, next one is progress, and then the parameter list. Right. The first step what we have to do is we have to update these values here. So these values are arrived from the basic equation that I shared in the PPT. So I just use these values here. So WF, which is equal to 2, and then W1 1, and then W32 T 0.35, W32 T 0.035, H 1.6, H1 0.8, and then R1 is 8, and then LF is 14, LF is 14, LF is 14, L1 is 4, L is 36, L is 36. So this is what the thing is, the L is 36. So after designing this automatically, so after updating this parameter details here, so you have to design, go into the design stage. So in the design stage, the first step is we have to create the ground. So at the bottom of the antenna, we are going to have the ground. So at the bottom of the antenna, we are going to have the ground. On top of the ground, we are going to have the dielectric. On top of the dielectric, we are going to have the feed line and the radiating element. So this is what the antenna is going to be comprised of. So first, we have to design the ground. So for designing it, so I will. Right. So for designing this window, we have to give 6 values for designing the ground or designing any part of the antenna. We have to give 6 values. First is x minimum, the next one is x maximum, and next one is y minimum, and next one is y maximum, the next one is z minimum, and next one is z maximum. Right. So these are the 6 values in order to design any part of the antenna. The first one is we have to design the ground, and then we have to design the dielectric, and next we have to design the feed line. This feed line is going to have 2 parts. One is this part, and another one is reduced part. So which is slightly of reduced width. So this is feed line 2. This is feed line 1, and this is feed line 2. And after that, the radiating element. And for radiating element, if it is rectangular in size, rectangular in shape, then all the 6 values is available. Since it is circular in shape, we are going to have 6 values, but the values are inner radius and outer radius. First one is outer radius, and next one is inner radius, and third one is x center, and fourth one is y center, and Z minimum and Z maximum will be there. Z minimum and Z maximum. When the radiating element is circular in shape. Right. So if it is going to be a circular, it is going to be this. Or if it is going to be a circular dimensions, like hexagonal or pentagonal or any other shapes, it is also the extension of the circular shape. Either it is a hexagonal, it is the extension of a circular shape. Or it is a pentagonal, it is also the extension of a circular shape. Well, again, for such type of structures, the values will be outer radius, inner radius, x center, y center, Z minimum and Z maximum. For all the square and rectangular shapes, the values will be x minimum, x maximum, y minimum, y maximum, Z minimum and Z maximum. So this is what we are going to give it during the design. The first part, what we have to do is, this is the actual antenna. This is the actual antenna backside. This is the backside of the antenna. So I will just keep it here. So the length is going to be W, length is going to be L, and width is going to be W. Right. So this is the ground. So in the first design, we are going to have the full ground. That is, the entire white color is going to be covered with the copper. That is the ground. The entire white color, which is the dielectric. The white color is the dielectric. On top of the dielectric, up to LF, we are going to have the reduced ground. So because of this, such color difference is there. So in the first design, what I am going to do is, I am going to have the entire dielectric to be covered by ground, and the dielectric length, width is going to be W, and length is going to be L. While the width of the ground is going to be W, length of the ground is going to be LF for our design, but this length of LF is going to be replaced by L in the initial design. So what I am going to do is, so the entire length is going to be ground. The entire length is going to be ground. So I am going to divide, right? I am going to divide this into 2 halves. This into 2 halves, and this is going to be W. This is going to be W. First, we are going to have the width W, right? So all the, you can, from the figure you can able to see in the x direction we have width. So width of the ground, width of the substrate, width of the feed line, width of the second feed line, every width, all the width is available in x direction. In the y direction it is going to be L, which is going to be length. All the length is available in the y direction. So x and x minimum and x maximum will be the width, y minimum and y maximum will be the length, z minimum then the z maximum is going to be the what you can say, which is the height, which is going to be the height of the substrate. So just I am going to divide this width. So total width of the ground is W. So I am going to divide this W into two halves. So this side is going to be W by 2 and this side is going to be W by 2, since the total width is going to be W. So when I'm going to consider this line as 0, automatically this side is 0 to W by 2 and this side is minus W by 2, 0. And from minus W by 2 to W by 2, the ground is available. So X minimum will be minus W by 2 to W by 2. Okay, and then y minimum, in the y direction we are going to have the entire length. So again the length is going to be divided into two halves. When I'm going to divide into two halves, then automatically the entire length is going to be divided into two halves. So when I'm going to consider it as 0, so minus L by 2, 0 is going to be one half, and from 0 to L by 2 is going to be the other half. From minus L by 2 to L by 2 it is going to be the length of the substrate, sorry, length of the ground. And from Z minimum, the ground is available at the bottommost. The bottommost is going to be the 0, and topmost it is going to be the T. T is nothing but the thickness of the copper. T is nothing but the thickness of the copper. Whenever there is going to be the conducting material which is made up of copper, I am going to assume that thickness as T, which is equal to 0.035, which is the standard thickness for the thin conducting substrate. Sorry, conducting material. For a thin conducting material, for a thick conducting material, it is going to be 0.35. 0.35. Right. And then what we are going to design is, we are going to design the dielectric. We are going to design the dielectric. We know that the length and the width of the dielectric is same. Then automatically the same value is going to be the x minimum, y maximum, and y minimum and y maximum is going to be there. But from 0 to T, it is going to be, from 0 to T, it is going to be the ground. From T to T plus H, which is the thickness of the substrate. H is the thickness of the substrate. From 0 to T, it is going to be ground. On top of the ground, it is going to be dielectric. On top of the ground, it is going to be dielectric. From T to T plus H, it is going to be the dielectric. So T to T plus H, it is going to be the dielectric. So all are case sensitive, so you have to replace it, T to T plus H. And next one is feed line. So from feed line, here is the feed line. We know that the width is WF. When you are going to divide into two halves, automatically from minus WF by 2 to plus WF by 2 will be the x minimum and x maximum value. Right? In case of y minimum and y maximum value, when you are going to design this feed line, the y minimum is available at this end, right? From this end to LF, it is going to be there. So this part, this end is already we know that the bottommost line is equal to minus L by 2 when we are going to divide into two halves. When we are going to divide the substrate into two halves, this line represents minus L by 2. So this line is going to be available from minus L by 2 to minus L by 2 plus LF. So we have to replace by minus L by 2 to minus L by 2 plus LF. And already we know that from 0 to T it is going to be the ground, and from T to T plus H it is going to be the dielectric. On top of the dielectric it is going to be the feed line, and feed line is also going to be made up of a conducting material. So it is made up of copper, and thickness of the feed line is going to be T. Therefore, the Z maximum will be the Z maximum of the dielectric will be the Z minimum of the feed line, and Z maximum of the feed line will be equal to T plus H. T plus H, right? In the second part, we already know that the width of the field line is W1, right? So when you are going to divide it into two halves, then automatically minus W1 by 2 to plus W1 by 2, right? And next one is, what we have to do is we have to have this length. So we already know that from what is this value? This value is minus L by 2 to minus L by 2 plus L. And from top of this only we are going to have L1 distance. So this value, the field line Y maximum will be equal to the Y minimum of field line 2, and maximum will be L by 2 plus LF plus L1. And field line 2 is also available at the same thickness of that of the field line 1. Right. So in this way, you have to design we have to give the values so that the design will be available at the CST software, right? So when this values, how to plot this values, when you are able to easily understand, any complex design can be easily we can design in the CST window, CST studio. Any complex things we can able to, complex design we can able to do it in the CST window. So if you have any doubts, we can clarify it here. Otherwise, we can move on. If you have any doubts, you can ask regarding this tabulation. I think, am I audible?
Yes, sir. In the chat, we don't see any queries related to this.
Okay.
But participants,
Okay,
again, if you have any queries, you can ask now.
Right, ma'am, I will continue. If you have participants, if you have any queries, you can just ask in the middle. I can clarify your doubts. Right, so this is what the design is about. And first, in the modeling section, we have the brick. So just click on brick, click on this working plane, just click on here, press escape, right? So the first thing what we have to design is we have to design the ground. So I am rename it as ground, and x minimum value will be equal to minus W by 2. So this value, this tabulation, I am going to share it here. So I am going to take these values and I am going to update it in the window. So, and x maximum is W by 2 and Y minimum is minus L by 2 and Y maximum is L by 2 and Z minimum is 0, Z maximum is T, right? So, and the material is not available here, copper, so you can load it from the material library. By clicking at the load from material library, you can able to have the material library window here. So just click on annihilate. This is a lossy material. So for the fabrication error and other environmental issues, we have to make use of the lossy material loaded here. So preview it. While previewing, you can able to clearly see the entire ground pad. Click on OK. So when the ground is made, in the component window, you can able to see the ground is available here. And the next step is you have to fix the substrate. Again, click on brick, click on working plane, press escape, and the brick, rename it as dielectric, or you can able to name it as substrate. Substrate is the right term. So minus W by 2, minus L by 2, P plus H, P2, P plus H, and the material, what I am choosing is, I am going to choose the FR4 material. So FR4 lossy I am going to choose, load it, preview it. So preview is exactly that. So click on OK. So the same values I have tabulated in the here. So minus W by 2, minus L by 2, T2, T plus H. So this is what I am going, minus W by 2, minus L by 2, T2, T plus H. Click on OK. So you can just turn it around and you can able to see it that the ground is exactly at the bottom of the substrate. They are exactly linked to each other. So in this way you can able to see it. So just click on front. And next thing is what we are going to do is we have to design the feed line. Again, click on brick, click on working plane, press escape, feed line 1. So minus W F by 2, W F by 2, minus L by 2, minus L by 2 plus LF, T plus H, T plus H plus T. The material you have to choose is copper. Preview it. You can able to preview it. Click OK. And again, the second feed line, click on working plane, press escape, rename it as feed line 2. The next step is minus W1 by 2, W1 by 2 minus L by 2 plus LF minus L by 2 plus LF plus L1. T plus H, T plus H plus T. Preview it. You can able to clearly see that is available here. Click on OK. And next, the circular patch. In circular patch, you have variety of shapes here. Just click on here. Click working plane. So if there is an outer radius. That outer radius is nothing but this value. The outer radius is nothing but the R1. So click on R1. When you are going to have some inner radius, then it's going to be, let us consider it as 6, inner radius as 6. So when you are going to have an inner radius, then it is going to be acting as a ring. It will be created as a ring, right? So on the Y center, I am going to choose it as 7.9, so which is the optimized value such that it is available here, and T plus H, T plus H plus T. Right, you can able to clearly see it is available here. So in order to make it as a circular disc, I am going to keep it as 0 on previewing it, so you can able to see. And you are going to have some values here, inner radius, then automatically it will have a ring like shape. So click on OK. Click OK. And material use is copper. Click OK. Right. So this is how you have to design the entire antenna. This is how you have to design the entire antenna. And the next step is you have to give the feed line. So at the bottom you have the ground and the dielectric. On top of the dielectric you have designed the radiating element and the feed line. For giving the input excitation, you have to zoom such that the microstrip line thickness is available like this. And there is an option in modeling called pick. You have to just click on pick, and you have to just click on this thickness such that the entire thickness is available, is changed into red color. It should not be like this or like this. It should be, the thickness alone should be changed into red color. By keeping it there, you have to double click on it. Okay, and just save it. Save the as a name. You can EOCH and just rename it similar to a Word document. Right here, you can able to see we have renamed the thing. And after picking up, just go to home. There is an option called macros. Click on this macros. So there is an option called solver. So there an option called ports. So there an option called calculate port from extension coefficient. Click on it. So there an option called microstrip or strip line is available. Different type of port excitation coefficients has to be calculated, and you have to calculate it and construct port from fixed phase. Just click on it. Close it. Now you have created the port and you have created the excitation signal. You have given the excitation signal. And the next step is you have to set up your solver. Just click on setup solver here in the modeling. Click on it. There is a window popped up. In that window, click on the normalized to fixed impedance. Normalized to fixed impedance. Just click on it and just start the simulation. Just start the simulation. In the progress window, you can able to see the progress of the antenna. right? So after this progress, all the data will be available here. All the results will be available here. You can clearly able to see the results. So after completion, after this progress, you can able to see the results here. And after the during the results itself, the messages can be viewed here, right? The messages can be viewed here, right? That we can so the it will take some time for design for completing the simulation. So in meantime, we can just go to the PPT and we can. I will share some details with respect to this PPT. And the term metamaterial is a term which is coined in the 1990s by David R. Smith. So this metamaterial is going to have the properties which is not readily available in nature. So negative permittivity, negative permeability, negative refractive index, negative impedance, like that. Such unusual properties is going to be achieved not because of its constituent or chemical combinations, but because of its periodic structure, right? So macroscopic periodic structures. So that is what the metamaterial is. So we have plenty of metamaterial types, out of which this multiple splittering, spiral, and Liberace resonators are the widely used. So multiple splittering resonator is nothing but we are going to have the ring-like structures. In the ring-like structures, we are going to have the splits here. So this splits and the gap between these rings is going to act as the capacitance, and the metallic ring is going to act as the inductance LNC combination. And here the spiral, the rings are arranged in a spiral manner, and Liberace resonator and the gap between the links is going to act as capacitance, and again the metallic rings is going to act as the inductance. This is what with respect to the spiral resonator. In case of Liberace resonator, which is similar to a multiple splitting resonator, but the major difference is it is going to have the splits at both the ends, and the adjacent rings have the splits at 90 degrees to each other, which is what the difference between the metallic splitting resonator and the Liberace resonator. And with respect to the splitting resonator, it is a magnetic resonance. The magnetic resonance is induced by splits in the rings and the gap between the inner and outer rings. So parallel LNC combination, this is the equivalent circuit. The two rings are strongly coupled with each other, right? So with respect to the capacitance, from where the capacitance and where the inductance are origin, the total capacitance is due to the splits and also the gap between the two concentric rings, while the inductance is arising from the conducting rings. So that is what the origin. And with respect to the physical dimension of the SRR, the effect of split width, if the width of the split is very high, is increased. So as a result, the capacitance is going to be decreased. When the split is going to be increased, the capacitance is going to be decreased. Whenever the capacitance is going to be decreased, which increases the resonant frequency. When you are going to design an antenna for 5 GHz, and in order to, with the help of splitting resonator, in order to improve the from 5 GHz to 5.1 GHz or 5.2 GHz, by increasing the split width, you can able to increase the resonant frequency. That is what the effect of split width. And then the effect of gap distance, the gap between the rings is increased. The increase automatically, the resonant frequency is going to be increases. And when the metal width is going to be increased, then automatically the resonant frequency is going to be the increase, right? Since the inductance is going to be increased, the resonant frequency is going to be increased. When additional capacitance is going to be there, the resonant frequency is going to be decreased. So this is what with respect to the magnetic resonance of the parametric influencing. There are various parameters which influence the magnetic resonance of the splitting resonator. Right. So what is the variations? What is the effect of variation, or what is the effect of number of by increasing the number of splits? So when you are going to have a single ring resonator, then automatically when you are going to increase the number of rings, when you are going to increase the number of splits, automatically the resonant frequency increases drastically. When you are going to increase the number of splits in the two rings, then automatically the resonant frequency is going to be decreases. That is because of the additional ring. By adding the additional ring, automatically the capacitance is going to be increases. So because of this increase, the resonant frequency is going to be decreases. This is what the effect of this splits. That's when I think, right. So the progress is completed and the message is available here. So there is no any error here. Just go to navigation tree. So in the navigation tree, you can able to see the port signals and the S parameters, right? Port signals and S parameters. So which is operating, which has a peak at 5.1 gigahertz, but actually we have designed it for 3.4 to in this frequency with the center frequency of 4 gigahertz, and we can just, what we are going to do is, the impedance is not that much good. The impedance is not that much improved. The impedance is not that much good. So in order to match the impedance, we are going to reduce the ground lag. We are going to reduce the ground lag. And before that, if anything is going to be altered, then automatically the simulated results will be get lost. So I'm going to rename. So create a new folder, S1 comparison, and I'm going to keep this result in order to compare my future results with the first result, right? So that I can able to have some details, better details. So what I'm going to do is, I'm going to design this antenna. I'm going to design this antenna. That is, the length of the antenna is equal to L. So for that, what I'm going to do is, I'm going just double clicking on ground, and again I can edit the list. So from minus L by 2 to minus L by 2 plus L plus L. On previewing it, you can able to see that clearly the ground is reduced. Click on OK. Close it. Right. So again, you just click on Start Simulation. So this value minus LF minus L by 2 to LF plus minus L by 2 plus LF is from. So here you can able to see the ground is available from minus L by 2 to minus L by 2 plus LF. So that is the only deviation. So previously we have given the value as y minimum as minus L by 2, y maximum as plus L by 2 for the entire length. Now the length is reduced to LF. So y minimum is minus L by 2, y maximum is minus L by 2 plus L. That is what the y maximum is. Okay. So here we have given this values here. So again, I think I have started the simulation. Yes, it is simulating. So again, we can go back into the PPT. So simulation will take some time. For that, in order to not to waste the time, I just moving around this PPT. Right. So with respect to the complementary split ring resonator, the basic difference is, with the split ring resonator, the rings is surrounded by the air, but here the air is, the ring is made up of air, and which is surrounded by the copper. So that is the dual, which is the CSRR, the complementary split ring resonator, is the dual component of the split ring resonator. And the thing is, the magnetic response is converted into electrical response. All the equivalent, all the design equations are one and the same, right? So nothing has changed. Only the magnetic and electrics are interchanged, right? So that is, the electric and magnetic properties are interchanged with respect to the SRR. That is what the complementary split ring resonator. Apart from this complementary split ring resonator, we have plenty of resonators like broadside coupled SRR and non-bi-anisotropic SRR. This is some of the non-bi-anisotropic SRR. So it is used to modify, which is the modified SRR, which is used to avoid the bi-anisotropy in order to have the good broadside coupling. So that is the what, and then the spiral, different types of spiral resonators is also available. These are some of the examples of the spiral resonators, and then the open splitting resonator. So with this resonator, the structure size is almost reduced by 20%, which is the advantage for the same frequency. That is the advantage here. Two rings is going to be there. One ring is excited, other ring is also excited with the displacement current. That is the advantage of open splitting resonator. And then the S-shaped resonator is, the both the splitting and CSRR is going to have the negative permittivity and permeability at different frequency bands, but at the same frequency bands it is not going to be coincide. In order to have such type of ensure that both the negative permittivity and permeability is going to coincide, this S-type resonators has been introduced. And then which is the omega shape, which is a C-type ring with the stop at the both the ends, which is also be used, right? So I think it will be completed, right? So here you can able to see again the message is going to be there. So just click on navigation tree, click on this, and here the S parameter is going to do. So just click and drag it here. Here you can able to see we have a very good input impedance from this part to this part, right? So this is full ground, and this is off ground, not off ground, reduced ground. Right. So here we can able to find out the all the different values. I will show it here. Here, right click on the graph. There is an option called show measure lines. You can just drag the measure line to -10 dB, and you can just place these two vertical lines such that it coincides at the points. From that, you can able to clearly see the operating range, which is from 2.89 gigahertz to 4.46 gigahertz, and the bandwidth is available is 1.57 gigahertz. That is the total bandwidth, and the resonant frequency, which is available at 3.59 gigahertz, which is the or 3.6 gigahertz, which is the resonant frequency, since it has the deep. And then you can able to find out what is the return loss value, which is equal to -13.69 dB, right? So all this information can be available from the S parameter graph. And similarly, the VSWR is also available just in the one-dimensional research. Just click on VSWR. So you can just plot the properties such that the VSWR value is from should be always less than 2. So I just make it as 3. Here you can able to see from the value at 3.61, it is 1.52 dB. The operating range, which is from the same operating range. So in the operating range, the VSWR value is less than 2. In the operating range, the VSWR value is from 2.83 to 4.53. The operating range is less than 2. This is what the VSWR is. From that VSWR and S11, we can able to clearly view that what is the effect of the what do you can say, what is the effect of this how whether your antenna is working or not, we can able to clearly see, right? So the resonant frequency here is 3.6. The resonant frequency here is 3.6. That is the maximum dip. This is the maximum dip. So 3.61. So the next step, what we are going to see is we are going to find out the radiations patterns and the various other parameters. For that, we have to first find out the resonant frequency, and after that, we have to right click on this field monitors, create new field monitor, and there you have to replace this value with the resonant frequency 3.61, right? So click on E field, apply, click on H field, apply, click on surface current, apply, click on far field, apply, and far field transient broadband, click OK. Just start the simulation. So it will take some time. In meantime, I will share something about the 5G communication. Right? So what is 5G? So 5G is the fifth generation mobile network. So it is the evolution of 4G LTE. So the 5G is going to meet a very large growth in data and connectivity. That is the major. In order to accommodate large number of users with higher data and higher connectivity, this 5G is initially designed. So this 5G is initially going to operate along with 4G networks, and the major advantage is going to be the latency. Major uh, 5G is going to find the major advantages about the latency. It is nothing but the fast response time to any issues, which is nothing but the 5G. And latency is the time taken by the device to respond to each other, which is nothing but the latency. So 3G is having a 100 millisecond, 4G is 30 millisecond, 5G is going to have 1 millisecond as it is latency, which is the requirement. Right. So whether the 5G is going to change the entire world, actually we have two types of bands. One is 5G sub 6 gigahertz band and 5G millimeter wave band. So both the bands is accepted by the worldwide. So in the sub 6 gigahertz band, it is from 3.4 to 3.6. Now it is upgraded to 3.4 to 4.2, and then with respect to 5G, it is millimeter wave, it is the 28 gigahertz band. So all the from 24.25 to 27.5 and 27.5 to 29.5. So these are the two different bands given by the it is worldwide accepted in order to make sure that 5G is implemented. So what is the advantage? Extreme mobile broadband, unlimited experience is going to be there. 100 plus Mbps whenever needed, and 10,000 more traffic can be there, and greater than peak data rate is about 10 Gbps, and critical mission communication, mission to mission reliability and radio latency is going to be less than 1 millisecond, and massive mission communication is also going to be there. Yeah, mission to mission ultra low cost, mission to mission communication is going to be ultra low cost, and 10 years of batteries is also going to be um, which is good in nature, that can also be there because of these reliability issues and latency advantages. And then 10 to 100 devices can be connected at a single time. So that is the major advantage. So this is the advantage, and this is the deployment given by the Nokia. So this is how it is going to be deployment. So we have the plenty of towers is going to be there. So from the towers, a complete 5G can be given to a particular cell. So plenty of towers is going to be initiated with respect to 5G. So 5G is going to work with 4G, right? 5G connection is established. The user equipment will connect to both the 4G network and the 5G network. 4G network will provide the control signaling, while 5G network will give the fast data connection. This is how it is going to be working initially. And when there is going to be limited 5G coverage, then automatically the data is going to be carried over the 5G network, right? So 5G network is going to complement the existing 4G network, not a new network is going to be created. So what is the scenarios and what is the key requirements and the key solutions? So massive growth in mobile data is going to be there. Higher data rate per user is going to be there, right? So massive growth in mobile data. So automatically the increase the spectrum frequency is the spectrum has to be increased, and higher data rate. So 700 megahertz of basic coverage is going to be established, and connected device is going to be there. 3.5 gigahertz of high data rate service and capacity is going to be there, and lower latency and real-time connections. We have two separate, one for data rates and another for capacity hotspots, separate data rates is going to be there. Higher efficiency battery life is going to there. Ultra dense networks can able to achieve a longer battery life, and connected cars, machine to machine learning, sorry, machine to machine communication. So everything will be done with the help of massive MIMO antennas for beamforming and spatial multiplexing. So just a second. So remaining, I think, right. So the again the simulation is completed, right? So warning, we cannot think of we are not in need of uh, thinking about it. So here in 1D results. So in 1D results, you can able to find out the electric field values at that particular frequency. So you can animate and see. And this is the magnetic field. Right, and the surface current. You can also able to find out the what is the surface current. So the surface current can be easily find out. So this is the surface current you can able to find out. So the metamaterial has to be placed such that the metamaterial is available at the maximum surface current. So you can place the metamaterial here so that it can be able to easily excite. Yes, you have to keep the metamaterial such that the maximum in the area where the maximum surface current is available. So this is the area where the maximum surface current is available and you to put, but this is the feed line. You can also include the metamaterial into the feed line, but I'm going to include it here, right, in the patch. I'm going to include it in the patch. So that is what the next step is, and the far field results can also be easily found out. The far field result, here the directivity and the gain can be found out. The gain is about 2.45 and the directivity is about 3.17. So by double clicking it, so you have the 3D radiation pattern. So here replace with the pi value as 0 and apply. This is the E plane and this is E plane and this is H plane. If pi is 0, this is H plane. Just a second. You have to make it as constant theta. So this is H plane, and if it is 90, it is going to be the E plane, right? So E plane is going to have an H-shaped dipole radiation pattern, and H plane is going to have the omnidirectional pattern. Constant theta. Omnidirectional pattern. This is how the radiation of the E plane and H plane has to be find out. E plane and H plane has to be find out in the CST software. And next step is what we have to do is we have to compute the gains. For computing the gain, just go to post processing, click on template based post processing. So here there is two stages. One is far field antenna properties. In the second step, you have the far field result. Just click on far field result. In the browse monitors, click on far field broadband, click OK. And the browse result also, click on far field broadband, click OK. In the all settings, just go to browse monitors, click on far field broadband, click OK. Far field results, far field broadband, click OK. Again, broadband evaluation range should be in 3D, and here you have to select gain IEEE, click on OK. And just click on evaluate. just click on evaluate. So this is how you have to check the value. This is how you have to check the value of the gain. Check the value of the gain initial. Right? It will take some few minutes, and after that we can just design. We can just include the CSRR, and then we can what is the S1 and just include the CSRR and check about the S1 and performance, and after that we just include the superstate, and then again the same results can be verified. Right. So it is completed. So just plot the graph from 0 to so here you can able to see the gain is above 1.5 in the entire operating, above 1 dB in the entire operating region, right? So at 3.6, what is the gain? So you can just uh, show in axis marker. So here the gain is about 2.449, which is the gain, which is the actual gain. In this way, you can able to clearly able to find out the gain, right? So I just going to save it in another name so that the results can be found out, can be compared. Save as antenna 2. So here the antenna 2 is changed. So I'm going to delete the fault field details. And also I'm going to in the post processing tab, I'm going to delete it. I'm just going to what I'm going to do is I'm going to include this structure. I'm going to include this complementary splitting resonator. I'm going to include this complementary splitting resonators into this. For introducing this complementary outer ring and inner ring, so what I am going to do is I have the dimensions which are the optimized dimension which I already designed with the help of equation, complementary splitting equations, and we have the in the Google itself we have the tab. We have websites where the calculations can be easily done, through which also you can able to do it. So, but with the help of Ito book is the best book for the meta materials. So from that you can able to find out the formulas. Uh, Using that formulas, you can able to find out the what is the dimensions, inner radius, outer radius, all the things, right? So I'm going to just go to home, modeling, click on this thing, just click on working plane, press escape. So the outer radius value here is 6.5 and 6.5, 7.9, P plus H, P plus H plus P. So in order to H a value, H a circle or H any shape, we have to make use of vacuum here. Preview it, if I able to preview it, click on OK. Click OK. Right? And unfortunately, I have right. And next one is again click on. We have to give the second ring. So just 5.5, and the second value is 5.5. Y center is 7.9. P plus H, P plus H plus T, and again vacuum. Just preview it. Again, the preview will be available. Click on OK. Click OK. Right. So this solid 1 and solid 2 is the rings. So just add this. In the modeling we have an option called add. Just add both the rings, and after that the solid 1, this is the radiating element. So from solid 1 we have to etch this solid 2. So just click on solid, and in boolean we have an option called subtract. Click on it and then press solid 2 and press enter key. Then automatically the solid, from solid 1, this solid 2 is edged out. In this way you can able to create the edging. And next step is we have to introduce the slits. For the introducing the slits, the slit width is 0.5 mm, and y minimum and y maximum values. The first slit is 0.5 and 2, that is this value, this slit, and the second slit is this 12 and 14 mm. So I have to do that. So just click on brick, press escape. The total value is 0.5. So I am going to divide into 0.25 minus 0.252 plus 0.25, and total it becomes 0.5. And y minimum and y maximum is, first for this thing, this slit, slit, it is going to be 0.5 and 2. So 0.5 and 2, and again it is going to be t plus h2, t plus h plus t. And here the slit is made up of copper. Preview it. Sorry. Plus p. Preview it. So just reduce to 1.8. Preview it. Yeah. So you can able to preview such that it is exactly over the first circle. Click OK. And again click on brick, press escape. So again minus 0.25 to 0.25. Again 12 to 14, t plus h, t plus h plus t, and just preview it. You can exactly see that it is exactly on the second. Click on it. And now what you have to do is you have to click this 3, that is solid 1, solid 2 and solid 3, and press add and click on it. Automatically the slit is created here. Just again start the simulation. So it will take some time. So in meantime, if you have any queries, you can ask. Otherwise, I can complete the PPT and then we can have the question and answer session. Right, I will complete this PPT and then we can have the question and answer session.
Sir, good afternoon.
Yes, sir.
Sir,
Yes, sir.
This is Kiran Chand, sir.
Yes, sir. Tell me, sir.
So I'm working on 24 gigahertz, sir.
Working at 24
gigahertz frequency.
Okay, sir.
Actually, I have designed 24 gigahertz microstrip rectangular patch antenna.
Okay, sir.
Using equations had it from Balani's book.
Okay, sir.
But it is resonating at 28 gigahertz, sir. How to get the exact resonant frequency? What changes I have to make to
Sir,
get the exact?
you have to just optimize your dimensions, sir. You need not again go back to any other equations.
Okay.
You just optimize your dimensions, it will definitely work out.
Okay, sir. Okay.
Yes,
Is there
sir.
any particular equations for
No,
to find the field dimensions?
Equations are the approximated equations only, sir. All the equations are not the exact equation; they are approximated equations. So we have to optimize the dimensions. That is the only way.
Okay, sir. Thank you,
Yes,
sir.
sir. Yes, sir.
Dear sir, it's me Sriram, sir. It's me Sriram.
Okay,
Sir,
sir.
sir, could you please teach us how to plot cross polarization versus frequency?
Cross polarization versus frequency.
Yes, sir. Yes. In
Sir, you have
CST
to go.
studio.
No, sir. In the polarization graph cannot be directly done with the CST.
Okay.
We have to go with the MATLAB based on some equations.
Okay. Okay, sir. Okay. Sir, and meanwhile, could you please show me that how to plot cross polarization graph
Cross polarization graph.
on the CST studio? How to plot cross polarization, sir? Because you have shown me the E plane and H plane. Could you
Yes,
please show? Could you please show me the cross polarization graph, sir?
yes, yes, yes. So, just a second. So it will be opening. I after opened up, I will show you. Right. So here the after the simulation is after including the CSRR, the simulation is completed, and the S parameter, what is the effect? You can able to clearly see what is the effect. So here the impedance by comparing this result in S11 comparison, we can able to clearly see that. So this is the reduced ground, and this is after including the complementary split ring resonator. So here we have a good impedance matching, and after that two bands is achieved at one at 5.9 and another one at 7.5 gigahertz, right? So a triple band is achieved with the after including the complementary split ring resonator. This is the advantage. And regarding your query, sir, so this is the sorry. Here you can able to see the cross pole and co-pole, sir. Cross pole and co-pole. So just go to linear omnidirectional. So without isotropic, you have to just go with linear and omnidirectional. Click on this polarization, and then you can go. You can have the cross polarization and co-polarization plots. That is the thing, sir. And again, when you are going to click on it, and then you are going to have the 0, you can have the results, co-polarization results, as well as and cross-polarization results. That's it, sir. And with the help
Thank
of
you,
MATLAB, you can yes, sir.
sir.
And with the help
Thank you. Thank you. Thank you, sir.
yes, sir, yes, sir. With the help of MATLAB, you can just plot the frequency versus cross and flow polarization. That's it.
Sir,
Yes, sir.
sir. If possible, can you explain at least a 2 by 1 array how to design if time allows?
Yes, sir, definitely, sir. Definitely. Sir, array
Oh,
is not at all an issue. So just copying and we can just paste it. The
okay.
same design. That is the thing.
Oh,
I will, if time permits, I will show you. Otherwise, I will just design it. And the simulation, all the process is the same process. I
okay.
will
Okay.
tell you explain it. Yeah.
Okay. Thank you, sir.
Thank you. And the next step is we have to design this shape, that is the superstate. We have to design this superstate. On top of this superstate, we have to design this periodic SRR rings, and the dimensions are already I have chosen it here, and the superstate dimensions is available here, right? So I'm just going to directly design it here. So just go to modeling, just click on brick, press escape. The dimension of the superstrate is minus w by 2 to w by 2, 0 to L by 2, t plus h plus t plus, t plus h plus t plus 1 to t plus h plus t plus 1 plus h1, h1 or 0.8, which is the thickness. So this is the thing. So from here, just I will zoom and tell you. So this is So this is 0 to t, and from t to t plus h, this is the substrate. From t plus h plus t, this is going to be the top of the patch and feeding. So this is what the thing is. That is from t plus t h plus t. This is from top. From here, from 1 mm up. From here, a 1 mm at a 1 mm distance, the substrate has to be started, and from there it has a height of h1. The h1 value I already plotted it as 0.8. Just preview it, you can able to view it. So this is what the substrate is. So from 0 to t, t to t plus h, t plus h plus t plus h plus t. In your this side, this has the distance of 1 mm, and this has the thickness of 0.8 mm, right? So click on OK, and it should be FR4, and material should be FR4. Click on OK. Right, so the superstrate is completed. The next step, what we have to design is we have to design the radius, inner and outer radius, inner and outer SRR ring on top of the. Here it is the value 3.53, and Y center is 5 and 2.52. That is the values. So just replace this 3.53 and 5, t plus h plus t plus 1 plus h1 control C control V plus t. Preview it. You can able to preview the round circle. Click on OK, and next again 2.5 to 2, again 5 and t plus h plus t plus 1 plus h1 control V plus t. Review it. So click on OK. The circle is completed, and the next stage what we have to do is we have to etch it. We have to etch the slits. We have to etch this slits, and for the slits, the width of the slit is 0.4 mm. So we have to use that slit. Just click on brick, press escape. It is equal to 0.2 minus 0.2 to 0.2, since it is 0.4 mm, and the value will be equal to t plus h plus t plus 1 plus h1 2 plus t, and the material is vacuum, and the value x center and y center, y minimum value is 0 to 2. So just preview it. So 2.2, just click on 2.2 so that it will be it is exactly matching here. Click on OK, and you also able to change. You can also able to transform the ring, transform this here by using right clicking the option. By right clicking the transform option, just copy it and move in this direction. So here you can able to see that it is available. So it is exactly at the second ring and this is at the first ring. Click on OK. So here you can able to see two rings, right? So this is the design. So this is the design. So what we have to do is we have to merge, we have to add this two vehicles. So click add. And next thing is you have to add this two rings. So just add. Click on boolean, just add. Now you have to etch this two rectangular slots in the ring. So in from click on solid 3, boolean, subtract it, click on solid 5, press enter. So automatically the circle is, yes, the splitting resonator has been created. So this is the splitting resonator. What next step we have to do is we have to create the periodic structures. So this periodic structure, click on this periodic structure, transform it and copy it in X side, preview it 8 in steps of 8, translation vector, make it as 8, preview it, apply, and again in Y side, preview it, apply, again in X side minus 8, preview it, apply, again minus 8 and plus 8, preview it, apply. Sorry, and one more thing we have to do, mirror, sorry, not mirroring, translate, copy, and it should be 8 plus 8 and plus 8, preview it and apply. So you need not, this is the simple option available in CST. You need not have to draw each and every part when it is a periodic structure, right? You can able to translate easily when you can have some design sense with respect to the X and Y and Z axis, right? So this is the superstate design. So again, you can able to clearly see this. So this is the thing. And next step, what we are going to do is in the field monitors, we are going to compare the gain, right? In the field monitors, we have to compare the gain. For comparing the gain, what I am going to do is, so far field results transient broadband. So for calculating the gain, this far field transient broadband is required. So I just click on it, click on OK, and then what I'm going to do is I'm going to just restart my simulation here. I'm going to just restart my simulation. So in meantime, we can just go back to the PPT and complete that PPT. Right. So in 5G, it is going to be the combination of all the voice, text, video, and live streaming multimedia. Right. So all the plenty of application is going to be available nowadays, and as well as the virtual reality, connected cars, augmented reality, everything is going to be there. So 5G can able to accommodate. It is not at all possible with the available spectrum altogether. That is up to sub gigahertz. Therefore, only the increase in spectrum up to 28 GHz has been advised for the 5G, and also in order to accommodate this millimeter waves, that is the 25 GHz, 28 GHz band and 25 GHz band is available, and small cells, massive MIMO, beamforming, and full duplex. These are the technologies adopted by the 5G communication in order to give a very good latency and very good data rate. That is the with respect to the 5G. And with respect to the millimeter wave, with respect to the millimeter waves, more people and devices are going to be there is available nowadays. When the bands are going to be very small, when the bands are going to be the very small, lesser bandwidth, and automatically slower devices may be slower, right? So there is a need of a new range which is not at all used, which is from 30 to 300 gigahertz, right? So their wavelength is from 1 to 10 millimeter, and hence it is called as millimeter waves. And this is the reason why the 30 to 300 gigahertz is widely used in the range, right? And this 6 gigahertz to 300 gigahertz is not at all used nowadays. The available band is from 3 kilohertz to 6 gigahertz. When there is going to be plenty of application within this 3 kilohertz to 6 gigahertz, the data cannot be the intended use of that application cannot be achieved, right? So in order to have a wide range of spectrum, the entire spectrum from 3 kilohertz to 300 gigahertz is open, which is nothing but the 5G communication, which is millimeter. But the major disadvantage of millimeter, they are easily blocked and they are easily absorbed by trees. That is the major disadvantage. And in order to overcome this, the cells, small size cells is going to be there. This is the base station, and a small size base station is going to be there everywhere for every 250 meters. And this station is this small size is going to act as a relay, receiving the data from the base station and relaying to the for the receiver and 8 ports for the transmitter. But 5G is going to be the 100 of ports. When there is going to be the 100 of ports, the major disadvantages is going to be very high, right? In order to overcome this interference, the beamforming technology is
Hello, Prasad sir. If you are hearing me, we are not able to listen to your voice. We are experiencing some audio difficulty. Dear participants, sorry for the inconvenience. We are keeping in touch with Prasad sir. He'll join immediately. Sir will join the program in some time. That you are requested to attend the exam, which is scheduled today evening at 7:30 p.m. It's a 30 minutes mandatory examination. Kindly note, the certificate will be issued only to the participants who secure 50% marks in the test. You may as well fill in the feedback form after the test. Thank you. Please stay online. Sir will join us soon.
Sorry for the interruption. I think I have some network issues.
Yeah, yes, sir. Yes.
Right. So this is after implementing the super state. After implementing the super state, so this is the S11 result, and I just drag it here. So here this is the full ground without full ground, and for impedance matching we have reduced the ground, and after that with the inclusion of complementary split ring resonator, we have achieved a triple band. So and with the help of super state, we have able to achieve a good impedance matching in all the resonating bands, right? And the next what we have to do is we have to calculate the gain. Just click on it, gain. So just far field result, go to far field result. So in browse monitors, okay, okay, and all settings, in all settings you have to click on broadband 3D. In browse results also you have to choose the far field results, and then gain IEEE, click on OK. So and now evaluate. So it will take some time. So in meantime, so I think that is from my side, and this is my details. So I have a YouTube channel, so you can just uh, look into it, which will cover up all the designs that I have been made and all the webinars that I have been conducted. I will be posting, sharing the videos in my channel, and I have a Telegram channel also. You can join there, and this is my number and this is my mail ID. You can just contact me with respect to any queries. I can just clarify if I know the details. Otherwise, I will share my share the expert details with you, and you can just contact them. And at this end, I want to thank two people. I used to thank everywhere. The first person is Dr. Ragan from NIT. So he is the reason why I have chosen the RF field as my area of research. He guided me in such a way that it that his way of approaching towards the RF is very much impressive, and because of that impressiveness, I have just come into this RF domain. And then I want to thank Dr. Pandishwari from ma'am from NIT Trichy. So she is my course metamaterial course guide. From her only I have learned a lot of things about the metamaterials and how to use the metamaterials and what are the advantage of using that metamaterials. So everything I have learned from her. At this juncture, I want to thank this two persons, and that's it from my side. And if you have any queries, you can just ask. In meantime, I think the simulation has been completed. Right, so here you can able to see the gain is about 2 in nearly all the entire bands, and some areas where it becomes 0, while maximum it is about 2 dBA. It is about 2 dBA without the in previously we have seen that the gain value is nearly above 1.5 in maximum in all the operating bands. So that is the advantage of using a super state. So you can have any super state. By optimizing this super state, you can able to achieve a very good gain. So that is the advantage of using super state. But the major disadvantage of using the super state is again the size. The size of your antenna is going to be increasing. That is the major issue with respect to super states. If size is not a constraint in your application, then automatically you can go with the super states in order to improve the gain. And with respect to the array, so you can just transform it, right? So with respect to the array, you just click on all the things and just transform it in X direction. Right. So here a 1 cross 2 array can be formed, right? And again you can give an input here, and you can able to resonate here. And the array feeding is different from this type of feeding. For example, I have just shown you how to design an array. You can just copy and paste and transform it so that the entire array can be formed easily, right? A unit cell can be converted into an array easily. But in case of feeding, with respect to feeding, we have a different technique for array. If time permits, I will share you with some other sessions, future sessions. I will share that with you. So that's it from my side. So if you have any queries, you can ask. And I also thank the TOCH, TIST Institute for providing me this opportunity. If you have any queries, you can ask.
Thank you, sir. So there are a few questions that our participants have put in the chat. We'll share it to you, sir.
Yes, sir. So how the effective area is going to be increased? So the effective area is going to be increased. If you are going to meander it, the actually if a rectangle of size, right, W cross W, W cross L. So the size will be somewhat I will show some meandering examples so that I can clearly explain to you. So let us take this as an example, right? Let us take this as an example. So if it is going to be a circular, right? So the current path will be somewhat like this, right? Around it. So if you are going to have these notches here, the electrical length will be increasing.
Sir,
yes.
Sir, we could not able to see your screen. So could you please share?
Oh, sorry. I think now you are listening.
Yes, sir.
Yes. So if it is going to be a simple circle, the electrical length is equal to the radius, right? A radius or a diameter. So, but if you are going to have some such meandering shapes, like a notches here, everywhere at the end of the circle, edges of the circle, you are going to have the notches. then the current length will be increasing, right? So if the current path length is going to be increasing, is nothing but the increasing in what you can say. Actually, the question is about. Can you share the question?
Yes, sir. I'll share it.
Right. The effective area of the antenna will be increased. That is the thing. The effective area of the antenna is going to be increased. And next one is, what is the extension coefficient of the port? Right. So you cannot able to place a port at the particular with the what you can say the feed width, right? So there should be some extension that can be calculated easily in order to avoid the losses, right? In order to compensate the losses. So simulating a UWB antenna in CST of my 16 GB RAM is taking a lot of time simulation. Also, sometimes simulation gets aborted due to insufficient RAM. How to open? So a 16 GB RAM is quite enough. I think some other installation issue will be there with respect to CST. CST, I think the CST is not completely. There may be some installation issues with this. Because of that, the simulation get aborted. So that may be a problem. And which software tool is preferable to design the antenna? So any software you can design with any software. But the thing is, you have to know from the equations you have to design, and in order to validate that design, you have to make use of the software tool, right? All the software tools is you can learn all the software tools and you can able to use it, right? All the softwares are very much easier. On comparing with some of the tools, this CST is somewhat user friendly, right? So in a single click, and we have plenty of things. We can, with a single click, we can able to achieve a wide range of results, right? So that is the only advantage on comparing with the other tools. The CST is somewhat easier to learn in a quick way, but HFSS is also easier, right? So the thing is, we have to validate with the software tool, right? You should not prefer to design an antenna, or you should not complete your research only with the design tools. That is the major thing you have to see. Right? Any other queries?
No, sir. Thank you. All the questions have been answered, sir.
Okay.
So
I think I left.
excuse me, sir. Yeah, this is Lingaswamy. So that question has asked, right, that memory is insufficient like that, because I have faced many times. So, so the one option could be they have to store the file in where the at least 100 GB, 70 GB space is available. They cannot just store in desktop, and if they run, then it will be difficult. Second point is they can reduce the mesh size. If it is an array, then they can reduce this mesh size as well as the number of pulses to be sent, and also accuracy. If you reduce it to certain extent, the results will not vary, but it can run. So that is the only. But if a single antenna is not running, means that is something fishy. So that is the 16 GB RAM means something. Some other games he could have installed. That is eating that all the memory.
Yes, sir. 16 GB RAM is quite good.
Quite large. In 4 GB RAM, we are running so many simulations.
Yes, sir. Maybe
so
you
one
can.
More, yeah. Okay, sir. Okay. So one more point I want to add here is, I'm sorry if I'm interrupting. So regarding 5G, you are telling that along with the 4G, they are going to implement, not individually. In 5G, there are two modes are there. One is non-standalone mode, other one is standalone mode. In non-standalone mode, it will be implemented along with the 5G. 4G will take care of control. 5G will only handle the data. And the standalone mode, it will be a unique 5G network, complete 5G network, where the 4G backwards support like voice and everything will be there. That is the second thing. Third point is like latency. You are telling us 1 millisecond. So 1 millisecond they could achieve in LTE advanced also. But 5G is going below 1 millisecond frame structure, making in such a way that even 25 nanosecond they are going in that way.
Okay, sir. Okay, sir. Thank you very much, sir. I will change my.
I'm working on 5G only. That's why I know this point.
Yes, sir. Maybe I may be wrong. So
no, not wrong. You have said whatever you told is correct. So there, that was up to release 14. So after release 15, 16, they upgraded all these things.
Okay, sir. Okay, sir. Okay, sir. I will change my PPT so that I will able to share the correct information to the participants.
You can refer 3GPP release 16 so that it will be updated one.
Sure, sir. Yes, sir. Thank you very much. Thank you very much, Linguswamy sir, for giving the details about the 5G. And I also thank the management of TOCS College as well as the Department of EZ, head of the Department of EZ, and then Perumal Segar sir for providing me this opportunity again to participate in such nice event. Thank you very much.
Thank you very much, sir. Yes,
and
sir.
thank you to all the participants.
Thank you, sir. Thank you for your time today, sir, and for sharing your insights on the subject with us. Thank you very much. As we have come to the end of the 6 days SCTP program, I invite Dr. S. Raghavan, sir, to say a few words about our SCTP program. Raghavan, sir.
Sir. Sir, Rahan, sir.
Hello.
Sir, welcome, sir. Please give words about our.
First of all,
we need your advice, sir. We need your advice.
I would like to know the name of the MC professor.
So my name is Shion P. Johnson, sir.
Oh, Shion. Okay, that first
Shion.
Name. Just you used to say that there are no words. For me also, there are no words of your way of doing MC. Maybe you would have got the practice from the school days. Anyhow, it's good.
Thank you, sir. Thank you.
The next, I thought I should not keep on interfere. That's why I kept quiet. But she called me. 1 or 2 sentences I will tell. First of all, I would like to tell all the participants that the person who presented just now practically, maybe I don't know whether the luck or his merit also, he got his paper accepted in a very good journal. And all are by his own merit. He never relied on there is no facility even, relied on NIT facility, there is nothing. But he relied on his own work. The way in which he fabricated, he himself did this analysis and got the paper accepted immediately after his last presentation. That was the luck of participating in talk. So that's why I'm keeping on joining in talk, whether Dr. Perumal Shankar calls me or not. Then I once again would like to tell enormous work contributed by the team. Dr. Perumal Shankar, Dr. Vinu, Madam Sri Lakshmi, Dr. Jobi, and some more people behind the screen, all have done exceedingly well. Exact time you point out. Only thing, if at all time exceeded, maybe my interference. Otherwise, you all maintained. And there was a very silent anchor behind all this strong team. And that person is no other than HOD, Dr. Elizabeth. She silently anchors them to get a big news. Everyone enjoys. And
yes, sir, it is true, sir. It is 100% true.
No, I can realize, I can easily see, microwaves can see through third eyes by mental telepathy. then also to the whole management team. I could hear the initial talks, wonderful talks by all the top management team. I really enjoyed, and many I was enjoying the conversation between Dr. Lingasamy Veluswamy along with our person who presented. Had a lively session on 5G. It's all good. Every session I kept enjoying, and even Dr. Mahadevan is so sincere. So today he didn't come. He sent one leave letter. I'm not coming there. So that way, all credit goes to the team members. I wish you all the best. Once again, I request HOD to approach the management and set up one good antenna measurement lab. Then many more will come to you for carrying out the measurements. Thanks to the team, and special thanks for not for allowing me to interfere now and then. Thanks a lot.
Dear sir, I'm Deepa speaking. Thank you so much for your kind words, sir. And as you said, we will surely take this matter seriously as what you have suggested. And thank you once again to all the distinguished resource persons who have taken sessions for us. And Raghavan sir, you have never been disturbing us. You have always been encouraging, and all your comments and suggestions have always been motivating us to go forward. So thank you once again, sir, on behalf of Turkish and the Department of Electronics. We'll now have a formal vote of thanks by Ms. Shion.
Madam, one sentence, madam.
Yes, sir. Yes, sir.
One sentence, madam, before the
Sure,
formal
sir.
vote of thanks.
Yeah.
You are the coordinator. You got every right. I'm telling you on behalf of the HOD.
Okay. Sir, before the vote of thanks, I'd like to say a few words about our most respected and honorable professor, Dr. Raghavan sir, because he fostered a sense of support and appreciation. So that encouraged me to conduct the STTP in a very good manner, because daily he used to give some advice, and through him only I could identify, that is, I could get the resource persons, that is giants in antenna technologies, Dr. Honorable Professor Dr. Surendra Pal and Honorable Professor Dr. Mahadevan, Dr. Honorable Professor Ravindra Misra sir, and so many people I identify, that is, I got it through our professor only. So that is the enlighten of this STTP. Those experts, their help and their wholehearted help, that enlighten the total value of this STTP, sir. So moreover, I can say, I wanted to say one thing, that is, our Raghavan sir always disseminates his knowledge to all whoever wants. And I remind myself of how he has been doing his extra round in shaping the researchers like Dr. Krishnakant and Dr. Shanmughanandam sir, like so many people. So they are all very genius in that area. That is only only by the support of that guidance of and advice of Sir Dr. Raghavan sir. So I'm very much fortunate to get his get a contact of Raghavan sir. That is after a long period. Then sir has helped a lot. That is from the deep down of my heart, I would like to thank Raghavan sir. So in the formal vote of thanks, they will tell thanks to all. But even though, I wanted to say my thanks to my most respected and honorable Professor Dr. Raghavan sir. Thank you, sir. Thank you so much. Thank you. We need your support in the third phase also, and our in future works also, sir. Thank you. Thank you so much.
Okay. With the permission of HOD, only one sentence I want to say. See, I have not been helping. I am a little bit selfish. Through your institute, I heard a stalwart speech. That is my interest. The second thing, I felt very much proud when the speaker today, afternoon speaker, told about Pandishwari. I'm telling to the HOD that Dr. Pandeshwari was my scholar, and she is the first person to do research on metamaterial, and definitely she does very well, and that's what our speaker has told about her. So these two I want to record. Maybe the wonderful MC speaker will show her talent again now.
Thank you very much, Raghavan sir.
Okay. And one more thing I'm telling, I'm not simply praising. If you ask the speaker, he will tell how much people don't like me because of my roughness. But why I keep telling about HOD is, in my experience, no HOD who belongs to the other field has remained till the last session. I have seen you attending as much time as possible, and to this fag end, normally no HOD remains. That is the strength you give to your team members. Wonderful.
Thank you so much, sir. Thank you so much for your kind words. So we have a great team. That is the strength of our department, and I'm always proud of that. So I have to be with them. That's it.
Okay.
Thank you so much, sir. We shall wind up with a formal vote of thanks. Shion Miss, can you please? Yeah.
Yes,
please take.
ஆமா எங்களோட வீட்டை மறந்துடக்கூடாது.
Good evening, all. My name is Shion Johnson. On behalf of the Department of Electronics, Kochi Institute of Science and Technology, its entire fraternity, and the organizing committee, I feel immense pleasure to take this opportunity to propose the vote of thanks. I believe God was gracious enough to grant us a week to interact on a virtual platform with some of the well-known warriors across the country. I extend our sincere gratitude to AICT for permitting us and granting us the fund to conduct the second phase of the STTP on the topic 10 Trends and Technologies of Antenna Design and its Research Scopes. I would like to thank our management for providing us with the guidance to conduct this STTP. Especially, I thank our founder director, Dr. K. Varghese sir, and President Dr. Alex Matthews sir, who spared the time from their busy schedule to grace this STTP. I would especially thank our beloved principal, Professor Dr. Preeti Teketh ma'am, for her unfaltering support and confidence in us. I take this opportunity to specially express my regards and gratitude to our HOD, Dr. Deepa Elizabeth George, for always encouraging us and proving opportunities to organize such events. It says, acceptance bears us up. It's like buoyant water to a swimmer. The more we trust what we are immersed in, the better we float, the more progress we make to the shore. The progress and headway of thoughts we witnessed these days were made possible because of a hand of trust extended by our renowned speakers when they accepted our call to join this STTP. The pillar of strength in this mega success, as you all would have realized, was our resource person, Dr. S. Raghavan sir. His unwavering support throughout the STTP took us well past the finish line in all its glory. Thank you, sir, from the bottom of our hearts. We were greatly honored and privileged to have Dr. Surendra Pal, Dr. D.C. Pandey, Dr. Rabindra Mishra, Dr. V. Mahadevan, Dr. P. Mohanan, Dr. R. Bhubadi Rani, Mr. Magesh Chand, Dr. Sandeep Kumar, Dr. A. Pragasarao, Mr. Swapnil Gaul, Dr. T. Shanmuganandam, and Mr. Prasad Jones in our STTP. We deeply appreciate the vibrant group of participants who chose to be with us and attended this STTP with great enthusiasm, making it a memorable event. I would like to thank the coordinators of this STTP, Dr. Perumal Shankar and Dr. Vinu R, for all the hard work they put in and for their leadership and constant support. My heartfelt thanks to the organizing committee for taking topics that really matter in today's age and time. I place on record our sincere gratitude to Mr. Manoj M. John and Mr. Jobby Varghese for all the technical support they rendered and for helping us to webcast our program through the college YouTube channel. Once again, I thank you all for being with us all through these 6 days. Have a wonderful day ahead. Even though we are separated by some boundaries, we will certainly remain one in our journey towards excelling in our own spheres and in innovating for all the social good. Thank you. Stay safe and take care. Again, a reminder, we have the third phase of this STTP scheduled for next month. We humbly request your cooperation and look forward to see you all. Participants, we have an exam at 7:30 p.m. today. The link will be shared via WhatsApp. It's a 30 minutes mandatory exam. Please fill in the feedback form after the test. Thank you once again. Wish you all the very best.
Thank you.